Hi, in this video, I would like to share about tuning of a PID controller, particularly on open loop tuning method. To start with, we just have to revisit the open loop control scheme and a closed loop control scheme. So, in an open loop control scheme, it always, I think it is always represented by block diagram. So in an open loop control system, we have a controller and then we have a final control element where when we put the stimulus input, we will directly get the output. On the other hand, for the closed loop control system, this one is the block diagram of closed loop control system. The major difference is for closed loop control system, we have the feedback element, which is in this case we have the level measurement. We come back to the open loop control system. Take a look at this example. Okay, we have an example of a closed open loop control system. We take a shower water heater as the example. So the input is the heater knob and the output is the hot water. Okay, so as a user, we're going to change the knob, the heater knob from heat level 1 to heat level 2. This is what we call as the manual input, or we call as a manual set point. But in terms of the output, we will get the changes of the water temperature from the previous temperature to the hotter temperature. Okay, that is open loop control system. Looking at the closed loop control system, so as I mentioned earlier, the closed loop control system, the major advantage or the major difference of the closed loop control system in comparison to the open loop control system is the existence of the feedback element. In this case, we have the level measurement. Okay, whereby the feedback element will provide the measurement of the output, and most of the time the output is basically the process value. Okay, a closed loop control system, it consists of a controller, of course, then it consists of a final control element. In this case, we take a tank water level as the example, and in terms of measuring the water level, we use the level measurement. So the input, we can change the input. Here we change from the input from lower to higher set point. We change to higher set point. Then the controller will calculate the difference between the new set point with the current measurement from time to time. Okay, and result from the controller calculation, the output of the controller will reflect the behavior of the final control element, which then resulting the response to the water level in the tank. So this is going to be done. This is what we call as the single loop control, single loop automatic control system. Okay. For open loop control system, okay, as I mentioned earlier, when we change the manual value, we're going to get the system response, and the system response is called as the S-curve, or we call as the open loop response. Okay, this is very important. This open loop response because we are in the topic of we are talking about the PID controller tuning using the open loop method. Okay, so using the open loop, we change the manual value for the input. We change manual value for the input, then we will get instantaneous output. Means the process output. And looking at the input, so this one is the input. So we can say that the input is changing at time 0. Okay, this is the initial time that the input change, and we have a response S-curve of the output. Okay, this is the S-curve of the output. from this particular response, input and output, we will get two parameters, what we call as the time delay and time constant, whereby time delay is basically the difference between t1 and t0, and time constant is basically the time taken from t1 to t2. So how can we get the t0 and t1, okay, as well as t2? So this is the output response, and we have the input change here. So from S curve, we have to draw the maximum tangent line here. This is basically what we call it the maximum gradient of the S curve. So we have to draw a maximum gradient which cross the initial value and the steady state value. Okay, this horizontal line is basically what we call as the steady state value. So the crossing of this gradient line to the steady state is, we call it as a T2. The crossing of the gradient, the maximum gradient line to the initial process value is T1, and the initial change which correspond to the input change is T0. So now we have T0, T1 and T2. So you just have to do a simple mathematics. So time delay is equal to T1 minus T0, and time constant is equal to T2 minus T1. Okay, and we're going to use both values, which is the time delay and time constant, in the looking for the parameter of the P, which is Kp, I, which is time of integral in second, and derivative time is again in second. We just have to plug those value in using the Ziegler Nichols tables. Then we will get the parameters for the PID controller. Okay, I'm also going to do the demonstration, and the demonstration setup I'm going to use, of course, I'm going to use the factory IO, Portal, PLCSIM Advanced, and MATLAB-SIMULINK. So I'm going to run the demonstration. I'm going to demonstrate to you. So the setting or the setup of the demonstration, I'm going to use the tank liquid level system. So I'm going to manually provide a variation of input, and we're going to have a look what kind of output we'll get. So the variation of input that I'm going to apply to the system is, we're going to have variation of step input. So these are the variation of step input. I'm going to have variation of step input. Okay, why I use variations of step inputs? Because I'm going to have an impression what kind of S-curve output that we're going to have at the different level of step input. So the first step input, I'm going to change from perhaps 0% of the tank level to 10%. After 400 seconds, I'm going to change from 10% to 20%. At 800 seconds, from 20% to 300%. And at 1200 seconds, I'm going to change from 30% to 40%, and the next second I'm going to change from 40% to 50%, and the next 200 seconds I'm going to change from 50% to 60%, and at time is equal to 2400 seconds, I'm going to change at 60% to 70%, and the simulation stop at second when t is equal to 2809. We are expecting that we're going to get the S-curve for each set point changes, each manual value changes. Okay, I'm going to demonstrate to in this video using the factory IO, MATLAB-SIMULINK, Portal, PLCSIM Advanced, and OPC server. Okay. From the simulation, I have demonstrated to you the tank liquid level system, whereby the input is the stair-like input, which variation between 10 until 70 tank level in terms of percentage. This is basically, the input is basically related to the opening of the control valve, and the blue line here is the output. So the output is this one is the output response, and the red line is the input, okay, which is basically regulated valve opening percentage. So when we manipulate the opening valve like a 10%, we get the tank level about a certain value here. Then after a certain time, you manipulate 20%, we get that the level is about I guess here is 8%, so on and so forth. Okay, looking at this one, yes, we can say that what we expecting, we got what we expect, which is the tank level. We have managed to get the S-curve for the tank level. Okay, so if I just consider the behavior or the response at t between 400 to 800, this is t in between of 400 and 800, which is the output is this one. And I also consider the response between 800 to 1200, which is this one. Okay, and we're going to construct the maximum gradient line, and then we're going to find the T0, T1, and T2. Yeah. For proportional only controller, we can use this table. This is Ziegler Nichols table for step test method. So we just have to plug these two value into one of the controller. For example, if we want to find a value for P only controller, so this one is for P only controller. So we have to set Kp is equal to tau over theta, which is actually this one is 18 over 2, which is 9, yeah, 9. And integral time, we have to set it to infinity. So we can set it to 999, which is a large number. Okay, and then for proportional plus integral, For proportional plus integral, we have to look at this one, okay, this row. So Kp is equal to 0.9 times 18 over 2. Tau I is equal to 2 over 0.3, and tau D is equal to 0. So this one is, just use your calculator, 0.9 times 18 divided by 2, so we have 8.1, and Ti is equal to 2 divided by 0.3, 6.67, and tau D is equal to 0. And the proportional, integral, and derivative controller for P plus I plus D, we have Kp, which is this one, okay, 1.2 times tau over theta. 1.2 times tau is 18 over theta. Okay, then time integral is equal to 2 theta is equal to 2 times 2, and derivative time is equal to 0.5 times 2, 0.5 times 2. Okay, so 1.2 times 18 divided by 2 is equal to 10.8. Integral time is equal to 4 seconds. So this one should be second, this one should be second, this one should be second. Okay, this one should be 0 second. Okay, and the steady derivative time is equal to 1 second. Okay, we're going to plug all these three values and all these three controller setting into our simulation, and we're going to have a look how our controller respond to the system. Come back to the simulation. So we have the Simulink window here. We have factory IO, which already connected to the PLC via Portal, and we have the trending graph, which the yellow color is stand for the set point changes, which is this one, and the blue line is basically the PV, the feedback or the level measurement of the tank. I also include the PV value here, as well as the error, and the error is basically the difference between set point and PV at any value of t. Okay, the procedure, we're going to start with proportional only controller. When we have to change the proportional gain to 9, the integral time to infinity, in this case I put it 999, and derivative time to 0. Okay, I think let me drain the tank. Let me drain the tank first. I'm going to drain the tank. When we finish draining the tank, means the tank is empty. I'm going to click run so that the simulation will utilize the PID parameter, which is P is 9, the integral time is infinity, and the derivative time is 0. I'm going to set this set point to maybe I think 40. Okay. So from the simulation with P only controller at a set point of 40% of the level tank, now the PV measurement is 35.3 centimeter, and we have the error about 4.67 centimeter. So the error is quite huge, but the PV or the response is now in steady state. So now we're going to look at the PI response. So the PI is 8.1. So the KP is P 8.1. TI is 6.67, and derivative time is 0. We're going to change set point to 60. So you can see here, this is the response for proportional only gain, and this one is for proportional plus integral. So the set point is 60. The PV now is 53.7, and the error is 6.28. If we can zoom to the response, you can see that the system is trying to get close to the set point. See, so the error is reducing over time.